Hey, what's going on guys? Tanmaya for Simple Snippets and welcome back to another video tutorial under operational research, especially the linear programming part. And in this video tutorial, we are going to be solving a word problem of linear programming by using the graphical solution. So in the previous two video tutorials, what we've been doing is we are converting a word problem into a linear programming problem by analyzing the question and forming the appropriate expressions in algebraic form. So that's what we've been doing in the past two videos. So if you have missed that video, you can check those videos out. Those are just formulating the word problem into a LPP problem. But in this video tutorial, we're going to be taking it one step ahead. That is, we're going to first formulate the LPP in terms of the algebraic expressions, that is the maximization equation and the constraints. And we are also going to be solving those algebraic expressions to find out what exactly is the maximum profit or maximum gain according to the question. So we'll read the question in a minute and we'll also find out the best case scenario using the graphical solution in this video. So with that being said, let's start off with today's topic. Okay, so as you can see on the left hand side, I have a big question. So I'm just quickly going to read it because there's a lot to cover in this video. So a firm produces both interior and exterior paint from two raw materials M1 and M2, and they have already given us the table. So we don't have to make the table in this case. So this will make it a little bit easy for us. Of course, we've seen how to formulate the table in the past two videos. So if you watch that, this should not be a difficulty for you. So this is that table. We'll come to the table in a minute. Let's first read the constraints. Now a market survey restricts the maximum daily demand of interior paints to 2 ton. So in the question, we have our first constraint over here that according to the market survey, there is a restriction of maximum daily demand of interior paints. So there are two products, exterior paint and interior paint, and there is a restriction of maximum limit of 2 tons on interior paint. Additionally, the daily demand for interior paints cannot exceed that of exterior paint by more than 1 ton. So this is one more constraint which is indirectly given. Moving ahead, the firm wants to determine the optimum or the best mix of interior and exterior paint that maximizes the total daily profit, and we have to solve this using the graphical method. So we also have to find out the actual profit. Okay, so coming to the table, let me just tell you what exactly we have in the table. So in the center column, we have the raw materials or the products that are manufactured by the company. So we have two products, exterior paint and interior paint. The max daily availability is also given over here. So in one single day, 24 tons of M1 can be used and 6 tons of M2 can be used. And for making 1 ton of exterior paint, we require 6 units of M1 and 1 unit of M2. Again, this is in tons. Similarly, to make 1 ton of interior paint, we require 4 tons of M1, that is raw material M1, and 2 tons of M2, which is raw material M2. Okay, so these are the two raw materials and these are the final products. Ultimately, the company is going to sell exterior paint and interior paint, right? So it is going to make some profit on that. So these green values are those profit margins which is given. So after selling 1 ton of exterior paint, the profit obtained is 5 rupees. Let's assume it is 5 rupees or $5 depending upon where you live. Similarly, the profit obtained by selling 1 ton of interior paint gives you 4 rupees. Okay, so this is 4 rupees and this is 5 rupees. So I hope you've understood the table. I'm not going to spend a lot of time because there's a lot to do, as I mentioned. So now let's first convert this entire word problem into a proper LPP problem. So the first step is we need to identify what is the maximization statement, because ultimately you have to maximize the profit, right? So that maximization statement comes from this row, that is the profit row. And before that, we have to make certain assumptions. So this is the assumption step. And in the assumption, we assume that let X and Y be the amount of exterior paint and interior paint to be manufactured by the firm. So because we want to convert this entire word problem into algebraic expressions and formulate the LPP, we have to make certain assumptions, and the assumption that we are making here is let X, that is this small alphabet X, be the amount in tons of exterior paint. So exterior paint is X and the amount of interior paint that we are going to make is Y. Okay, so this is X and this is Y. So make sure you remember this X and Y, that is X is for exterior paint quantity and Y is for interior paint quantity, because we need to use them when we move ahead in this problem. Now after making this assumption, now we can calculate the profit, and the profit is given as follows. So the profit equation can be given as maximize Z or Z equal to 5x plus 4y. So what is this? So 5 is the profit earned on 1 ton of exterior paint, and X is the quantity which we are going to assume. So the total profit would be 5 into that quantity, right? So this is for exterior paint, that is 5 into X. Similarly, 4 is the profit earned on 1 ton of interior paint. So on Y tons of interior paint, we will earn 4 into Y profit. So this is that part. So this is that maximization equation. And lastly, as I mentioned, we have certain constraints that we read in the word problem. So let's try to denote them in form of inequalities, or also known as algebraic expressions, which have inequalities because they're not exactly equal. They are less than equal to or greater than equal to. So let me just put them out. So these are the constraints. So the first constraint is 6x plus 4y is less than equal to 4. So this constraint is material 1. That is, it is for this entire row, because you can see from the table the maximum daily availability of material M1 is 24 ton, right? And we are going to be using 6 ton for 1 unit of exterior paint and 4 ton for 1 unit of interior paint, that is 1 ton each for each of these products. So ultimately it is going to get over, right? So we have a limit which is 24. So 6, that is M1 required for 1 unit of exterior paint into the quantity that we assumed, which is X, plus 4 into the quantity of interior paint that we've assumed, that is Y, has to be less than equal to 24. So this is constraint number 1. It makes sense, right? I hope you're understanding this. Similarly, the second constraint is for material M2, which is 1x plus 2y should be less than equal to 6. So in the same way, we have constraint on material M2. Now the third and fourth constraint are given in the word problem. So for third constraint, you can see this statement over here. So according to the statement, a market survey restricts the maximum daily demand of interior paint to 2 tons. So interior paint quantity is represented by Y. So the maximum daily demand is equal to 2 ton or has to be less than 2 ton. Okay, so that's the limit. So it has to be less than equal to 2. That is why this less than equal to sign. And Y is the quantity that we've assumed that we are going to make for interior paint, right? So this is constraint number 3. And lastly, for constraint number 4, you have to see the next line over here. So this is the constraint number 4. That is, additionally, the daily demand for interior paints cannot exceed that of exterior paints by more than 1 ton. So the difference between interior paints and exterior paints cannot be more than 1, right? So it has to be less than or equal to 1. So Y minus X. So Y is the quantity of interior paints and X is the quantity of exterior paints. So the difference between the two cannot be more than 1. So it has to be less than equal to 1. So this is the fourth condition. And ultimately, of course, X and Y are going to be greater than equal to 0 because they are quantities. They cannot be negative. We cannot make minus 5 tons of exterior paint. That doesn't make sense. So that's why X and Y is greater than equal to 0. So this is the entire formulation of LPP, and we've already done this in the previous 2 videos. So that's why I kind of took it a little bit fast. Now moving on to the graphical solution, because we want to actually find out the actual profit, which is going to be the highest profit, and the optimum solution, that is the actual quantity of X and Y, that is exterior paint and interior paint, to be produced to get the maximum profit. So these 2 things are supposed to be found out using the graphical solution. So starting off with the graphical solution, the step number 1 is to convert these inequalities into equations. So when I say we have to convert all inequalities in constraints with equalities, I just mean that we have to remove this less than or greater than equal to sign from all these expressions and make it a proper equation. Okay, so you can see all these signs are being removed and now we have 4 proper equations. So this is step number 1. So the reason why we do it is so that we can map these lines on the graph. So basically each equation is actually a line on the graph. So we'll come to that in a minute. Let's move on to step number 2. So step number 2 is to finding 2 coordinates from all the equations to plot lines on the graph chart using assumptions. Okay, now since we're using graphical solution, what we're going to do is we're going to be plotting a graph which is going to be a 2D graph which will have x-axis and y-axis, because we've assumed 2 variables x and y. Now these can be x1 and x2 also, but just to make it a little bit simple, I've assumed 2 different letters so that you can easily make out the graph which will have the x-axis and y-axis, because we're used to x and y-axis and we're not used to x1 and x2. But sometimes in problems you can also get x1 and x2. Basically the name is only different, but ultimately they are the same. But for simplicity, as I mentioned, I've taken 2 different alphabets. So yeah, we're going to be plotting coordinates on the graph to plot these lines. And as I mentioned, each of this equation is basically a line on the chart. So that's how these equations work. And to find out the coordinates on the graph, what we have to do is we have to make certain assumptions. So let me just first open the graph as well. Okay, so as you can see on the right hand, we have a graph which is having x and y axis. So this is going to be the x axis, which is horizontal, and this is going to be the y axis, which is vertical. Now, as I mentioned, we have to plot the coordinates. So let's start off with first equation, that is 6x plus 4y is equal to 24. Okay, so as you can see, we're using this equation 2 times because we want 2 points on the graph to plot a line. Of course, to make a line, we need 2 points, right? So that's why we're using the same equation 2 times, and we're making a particular assumption, as I mentioned. So first time what we're doing is we're saying let x equal to 0. So this is something that we are assuming. So the x coordinate we are assuming 0. So when we substitute 0 over here, we are remained with 4y equals to 24, right? So 4y equals to 24, which means y is equal to 24 by 4. So this 4 is going to be coming in the denominator. And then ultimately 4 ones are and 4 6 are. So that's why we get y equals to 6. So x and y is going to be 0 and 6 because we assumed x as 0 and we got y as 6, right? Similarly, for the second time, we are going to assume y as 0. So for the first time we assumed x as 0, second time we are going to assume y as 0, and when we substitute y as 0, we get 6x equals to 24, and we'll be doing x equals to 24 upon 6, so 6 will be going in the denominator at the RHS, and then we'll be left with x as 4. So here we are getting a coordinate of 4, 0. So now let's simultaneously plot this line on the chart as well. Okay, so for the first coordinate we have x as 0 and y as 6. So x 0 means at this point and y at 6 means on the vertical line over here, right? So this is that point. So I'm just gonna mark over here 0, 6. Similarly, for this point, I'm just gonna mark it on the graph, that is 4, 0. So 4 is the x-axis. So 4 and 0 means the vertical value, which is 0. So this is that point. So I'm just gonna write over here 4, 0. So using this, I'm just gonna actually plot the line, and I'm just gonna write the equation of the line over here just for reference. So the equation is 6x plus 4y is equal to 24. So this is how you plot the line on the graph using the equation. So this was for the first line. What I'm going to do is I'm quickly going to show you 2, 3 and 4, and then we'll again plot them on the graph quickly, because the same process is going to be applied for equation number 2, equation number 3 and equation number 4. So let me just quickly show you equation number 2. So for equation number 2, again we are first assuming x as 0, we get y as 3. So we get the first coordinate 0, 3. Over here, second time we assume y as 0, so we get 6, 0. It's pretty basic. You can even calculate it if you are noting this sum in your notebook or somewhere. So it's very easy to calculate. Let's plot this on the graph. So 0, 3 is gonna be 0 on the x-axis and 3 on the y-axis. So it is over here. So 0, 3, and 6, 0 is 6 on the x-axis, which is over here, and 0 on the y-axis, which means this exact point. So again plotting this line, and I'm gonna write the equation over here. So 1x plus 2y is equal to 6. Now for the third equation, so third is a special equation wherein we only have one variable. So whenever you have one variable equation, it's a straight line. So when it is y equals to 2, it just means we have to traverse 2 from the origin, which is 0 over here, and we have to go 2 places above because it is a positive number, and then it is going to be a straight line which is going to be perpendicular to the x-axis. Okay, so this is a special line. Similarly, if you had x equals to 3, then the line would be something like this, a straight line which is going to be perpendicular to the y-axis. But right now we only have y equals to 2. So I hope you get this. I'm just going to write y equals to 2 over here. And lastly, we have y minus x equals to 1. So this was line number 3 or equation number 3, which we plotted in red. And lastly, we have the fourth line, which is y minus x equals to 1. So in this case, when we assume x as 0, we get y as 1. So we get the first coordinate as 0 and 1. But the second time when we assume y as 0, we get x as minus 1. Because you can see there is a minus sign over here. So the next coordinate that we get is a negative x value and a 0 y value. So let's just plot this and plot the line. So 0, 1, which means 0 on the x-axis and 1 on the y-axis. So this is that point, 0, 1. And minus 1, comma 0, which means minus 1 on the x-axis and 0 on the y-axis, so we're not going down. So this is that line. So if you plot these 2 points, this is something that you get over here, right? So when you make a line by joining these 2 points, this is that line, and the equation for this line is y minus x equals to 1. Okay, so now that we've plotted all the points on the graph, there is something that is known as the feasible region. Let me first just mark the feasible region and then I'll tell you what exactly it is. So this entire region, which is enclosed by all the lines, is actually the feasible region. And the reason why it is known as the feasible region is because any point inside this region is going to satisfy our maximization statement or main maximization z condition, which is z equals to 5x plus 4y, right? This is our original maximization equation. You can check it out over here. See this equation, this is that equation. Okay, so now we've plotted all the lines on the graph, all the coordinates, and we've made the lines of these equations. We also know the maximization equation, that is 5x plus 4y. So how do we go about finding the actual solution? So typically when it is a maximization problem, the coordinates or the value of x and y, so ultimately x is the quantity of exterior paint and y is the quantity of interior paint, right? So on the graph, the coordinates x and y denote those quantities. So we want to find out the best possible quantities that will give us the maximum profit, right? That's the optimum solution. So typically when it is a maximization problem, the best outcome is at the edges. So this is edge number 1, which I'm plotting in big white circle. This is edge number 2. This is edge number 3. This is edge number 4. And this is edge number 5. So whenever it is a maximization problem, as I mentioned, the best possible case or the optimum scenario is going to be obtained from these 5. So either 1 or 2 of them are going to give you the best case scenario. So let's name these coordinates first and then we'll find out the values of these coordinates. So for this coordinate, that is the first coordinate, I'm going to name it as A. For this coordinate, I'm going to name it as B. This one I'm going to name C. This one I'm going to name D. And this one I'm going to name E. Now out of all these coordinates, we already know the value of A and we already know the value of E because they are on the x and y axis, so we can easily find out the points. So with this information, let me just first make the entire table and let's just understand what that table is. So this is that table of extreme points. So all these extremities, that is A, B, C, D and E, I have listed over here, and I've also listed F, which is at point number 0. So usually this doesn't count because when x and y is 0, 0, that is the quantity of interior and exterior paint is going to be 0, 0. We're going to earn a profit of 0. So you can exclude this entire case, but I just mentioned it. So for A, that is this coordinate, we know the value is 0, 1. So 0 is the x value because it is on the y axis, and then just 1 point above, the y value is 1. So this is 0, 1. So coordinate of A is 0, 1. Now if we substitute 0, 1 in the maximization equation, that is if we substitute 0 over here and 1 over here, the value of z will be 4. So this 4 is actually the profit value. Okay, so this is 4 rupees or $4 or whatever currency that you're using. Similarly, we know the value of E. So this is that E point which is on the x-axis. So it is 4, 0. And if you substitute 4 instead of x and 0 instead of y, so we get 5 4s are 20. So this is 20 rupees. Okay. So we know the value of E and A, but we don't know the coordinate points of B, C and D because they are in between of the graph, right? So how do we find these values of B, C and D? So this is where solving simultaneous equations concept of algebra comes into picture. So the way we find these values is by using the concept of simultaneously solving the equation. So let's move on to what is simultaneous equations. Okay, so we want to find out the coordinate points of B, C and D, right? So we don't know the XY values of B, C and D, but we know that 2 lines meet at point number B, 2 lines meet at point number C and 2 lines meet at point number D, right? This is something that we know because this is where the lines are intersecting, right? So now using this concept, let's first find out the values for x and y for coordinate B. So for coordinate B, the lines that intersect at B are y minus x equals to 1. So this is the first line, and y equals to 2. This is the second line. So this red line is the second line, right? So this is y equals to 2. So these 2 lines meet at point number B. So in order to find out the value of B, what we have to do is we have to use these 2 equations and we have to solve them simultaneously. That is, we have to use value of one equation in another one. And the way we do it is you can see from 1 and 2, we already know the value of y, right? So y equals to 2. So we can substitute this 2 in the equation number 1. So after substituting y equals to 2 in equation 1, we have 2 minus x equals to 1. So x will go over here. So 2 is equal to 1 plus x. So x will be finally equal to 2 minus 1. So x will be 1, right? So here's how we get the coordinates for b, that is x comma y is equal to 1 comma 2, right? Because we already know y is 2 and we just found out x as 1. So this is that coordinate value of b, and this is how you solve two equations simultaneously to find out the intersecting point. Okay, so this is something which is a concept of algebra. Similarly, let's find out the value of coordinate c. So this is coordinate c, wherein line number y equals to 2 is meeting with this blue line whose equation is 1x plus 2y is equal to 6. So that's why these two lines. So this is 1 and this is 2. Again, we know the value of 2. So we'll substitute y equals to 2 in equation number 1. So we will get 1x plus 2 into 2 is equal to 6. So this would be x plus 4 equals to 6, and ultimately x would be 2 because 4 will go here and 6 minus 4 is going to give you 2. So we got x and y value as 2 comma 2 over here. So even from the graph you can see, right, that it is exactly 2 comma 2 because x is 2 and y is 2 over here for c. And lastly, for coordinate d, which is this coordinate, you can see that the line 1x plus 2y is equals to 6 is intersecting with 6x plus 4y equals to 24. So now we do not have direct solution over here. So what we'll do is we'll multiply this equation number 1 throughout with 2. Okay, so multiplying equation number 1 throughout with 2, we will get 2x plus 4y is equal to 12, right? If you multiply this throughout, we get this equation. And now what we can do is we can subtract this newly found equation from equation number 2, so that 4y and 4y will get cancelled, and when we are subtracting, the signs will change. So this plus 12 will become minus 12, this plus 2x will become minus 2x. So 6x minus 2x, we have 4x plus 4y minus 4y will give you 0. So this y gets cancelled, and 24 minus 12 will give you 12. So x is gonna be 12 by 4. So x is gonna be 3, right? So now that we've got 3, we still don't know y, right? So we can substitute x as 3 in any of the equation. So what I'm gonna do is I'm gonna substitute x equals to 3 in first equation. So we get 3 plus 2y is equal to 6. So 2y is equal to 6 minus 3. 2y is equal to 3. So y is gonna be 3 by 2, which is gonna give you 1.5. Okay. So of course, integers with decimal point is also valid in graph. So you just need to know where exactly to plot it. So we found x as 3 and y as 1.5. So let's fill out these coordinate values in the table. So for b, we found out x and y as 1, 2. For c, we found out x and y as 2, 2. And for last d, we found out x and y as 3, 1.5. Now using these coordinate values, so basically this x and y is the quantity of exterior paint and interior paint, right? So x stands for exterior paint and y stands for interior paint. So this is what we assumed initially when we first began the numerical. So that's why I told you that make sure you make a note of what is x and what is y. So x is the quantity of exterior paint, y is the quantity of interior paint. So now using this table, we can find out the maximum value, right? So we can substitute 1 and 2 in this equation. So when I substitute 1 and 2, z becomes 5 into 1 plus 4 into 2, right? And that will give you a total of 8 plus 5, which is going to be 13. So I'm going to write 13 over here. Similarly for c, when I substitute 2 and 2 as x and y values, so 5 2s are 10 and 4 2s are 8. So 10 plus 8 again 18. So this is 18 rupees. And lastly, when I substitute 3 and 1.5 as x and y values respectively, we get 5 into 3 is 15 plus 4 into 1.5, which ultimately will give you value of 21 because 4 into 1.5 is 6. So this is that last value. And now if you observe from this table, the maximum profit earned is over here, right? And the maximum profit is 21 rupees, which is achieved only when 3 tons of exterior paint is made and 1.5 tons of interior paint is made. So this is going to be your final answer, and the final answer is going to be max profit of rupees 21 can be achieved. So you can replace max with optimum also because it's an optimization problem. That is, optimum or maximum profit of rupees 21 can be achieved if 3 tons of exterior paint is made and 1.5 tons of interior paint is made. So this is going to be the final answer, and this is the optimization solution to this entire numerical. And I hope you've understood the entire process of how to first formulate the LPP, how to plot the points on the graph and then draw the lines for the respective equations, and how to find out the coordinates when the coordinates are in the middle of the graph. Also, I hope you understood that the optimum points are going to be the points which are going to be at the extreme ends of the feasible region. And I hope you've also understood what is the feasible region. So whatever values inside this region are also going to satisfy all the constraints. So in fact, you can take any of the point and substitute that coordinate value into the constraint which we had initially plotted over here. So you can take any of those points that we just plotted on the graph which are in the feasible region or at the boundaries of the feasible region, and you can substitute those values in these constraints, and you can see that it will satisfy those constraints. So that's it for this video, guys. I hope you understood the entire solution of LPP problems using Graphical Solution and the entire process of how to go about a maximization problem. So if you like this video, please give it a thumbs up, share it with your friends, and if you haven't yet subscribed on the channel, make sure you subscribe so that you get notified whenever I upload a new video. So thanks for watching, guys. I'll see you guys in the next video. Peace.